The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, and welcome to the SOLIDWORKS 22-minute webinar, Validate Drone Before It Takes Flight with SOLIDWORKS. My name is Ron Fermanic, and I will be your host. We would like to jump right in and get started, as we have a lot to cover in 22 minutes. A couple of items I wanted to point out before we get started. First, in using GoToMeeting, please notice the full screen button to move in and out of full screen mode. We suggest using full screen mode for the demonstration. If you have questions during the presentation, seconds per question to answer. Please note that you'll be able to download a recording of the webinar after the presentation. We will send you a link to that. And with that, I wanted to introduce you to our presenter today, Omar Zoni. Dr. Omar Zoni is a simulation technical manager at SOLIDWORKS and previously worked at ANSYS, where he was coordinating on multi-physics analysis. He has been in the industry for over 16 years, working for such companies as Northrop Grumman, where he was responsible for the thermal, mechanical, and vibration analysis of their electronics enclosures and boards. Dr. Zoni has a Bachelor of Engineering degree from the University of Pittsburgh, a Master of Science degree in Mechanical Engineering from Johns Hopkins University, and a Doctor of Philosophy in Mechanical Engineering from North Carolina State University. With that, I'll turn over the presentation to Dr. Omar.
Hey guys, thanks Ron. Thank you for that introduction. You know, as Ron mentioned, we have a lot to cover here in the next 22 minutes, so I don't want to waste a lot of time here up front getting started, but so let's hop right into it. So, you know, it should be rather obvious to anyone on the phone why we decided to cover drones this morning and this afternoon, right? The popularity of drones in the last handful of years, particularly the last couple years, has really just exploded. And if you guys go to, you know, Google and just do a Google search on like drones or drone popularity, there'll be so many different articles that you know, will come up, between Amazon delivering packages with drones, you know, drug cartels trying to deliver their drugs into the U.S. with drones. This past weekend there was a huge fire. I don't know if anyone lives in Southern California, but there was a huge fire on the I-15 at the El Cajon Pass, which is a major throughway from Los Angeles to Vegas. And as the firefighters actually had to stop fighting the fire via helicopters because some people were using drones to try to get footage of exactly what was going on. So, you know, lots of good and bad places where, you know, drones are being used. So we're going to be focusing today on SOLIDWORKS simulation, so not so much the design, but more the design validation aspects of drones. And there are lots of different ways or tools that and types of studies that you can use to validate your drone and your drone's performance. Specifically today, we're going to be focusing in on the CFD portion, so the computational fluid dynamics. We're going to talk a little bit about the finite element analysis also. But, you know, just to kind of point out, if you, you know, a lot of these cheaper drones that you can buy on like Amazon, you know, for personal use, a lot of the parts are made of plastic, and, you know, if you're in the manufacturing of drones, you know, and they're made of plastics, you can probably look at SOLIDWORKS plastics to do the injection molding, and there are tons of places where you could potentially use SOLIDWORKS motion. And obviously there are places where you can couple all or multiple aspects of these to kind of do some multi-physics types of applications. All right, so that being said, let's hop into the first poll question, Ron. And as you guys are answering this one, again, make sure you answer it via the polls, and we'll give you guys about a minute. And while this is going on, I will answer some questions if there are any. And we'll just, Ron, let me know when you're...
Yeah, the only comment I see, Omar, so far is that someone says your mic needs to be turned up, but no questions at this point. You're coming across fine to me. We're a little over 60% voted. We'll give everyone about 20 more seconds. And again, make sure you select one choice. I know we did this earlier today, and someone said it's maybe more than one, but we're just looking for one answer here on this question. And we just got about 5 more seconds. We'll do a quick view of the poll, and then we'll move on to the next slide. All right. Let me just do a quick share. So of our attendees today, pretty similar to what we saw this morning. But here we have trial and error is the best, or best guess is the most current way people are validating. We can help them with that, Omar.
Yeah, okay. So let's move along. So if you guys are anything like me, I am extremely poor with directions. So I used to live on the East Coast, moved to Maryland, and then moved out here to Southern California. And I'm old enough to remember when you used to have those maps that you kind of had to page through if you wanted to find your direction to places. Then we kind of moved to like individual GPS systems. Now no one has those, right? Everyone uses their phone to get to the best design. The reason I'm bringing that up is that's the most beneficial or impactful way to use simulation is to really help you navigate to the best design. So do as much design validation up front before you actually do start building prototypes, which can be expensive, right, and time consuming. The things that we're going to show you today are very, very fast ways that you can gain a lot of initial insight into your designs. And basically, we're going to look at 5 different things. So we're only going to be spending a few minutes on each one. We're going to be going real fast. I apologize for that in advance. If you guys have questions, you can reach out later. But I want to touch on a lot of different things. So the first thing that we're going to look at, the first model, is just a basic drone and what I'm going to call a wing study. So here is the drone that we're going to be looking at. You can see, it's a very simplistic version of a drone. I will explain to you guys why there are these cylinders going around them. But, what I want to do for this first example is I want to kind of walk you guys through the setup of how you would set up a flow simulation model. So flow simulation is turned on via the SOLIDWORKS add-ins. And that's the same place where plastics, motions, or the FEA solver is turned on. So, and one of the nice things that's available inside of flow simulation is what's called a wizard. Now, this wizard walks you through all the prerequisite steps required to set up and run a simulation. So I am not one of these people who are huge fans of like installation wizards. Probably no one on here is, because all you do is sit there and press next, next, next. No one's reading anything. That is not how the flow simulation wizard is. So I'm going to call this flow run, live run. And it's going to ask me, hey, what configuration do you want to use? So the flow solver, the flow file management is very configuration. Like if you utilize configurations inside of SOLIDWORKS, your flow simulation is going to sit right underneath your CAD configuration. Now the next thing that it asks, all right, what unit system do you want to use? And for those of us that are based here in the U.S., you know that we're very tied to our U.S. unit system. We're not a huge fan of metric. I'm not quite sure why, but that's the way it is. So I'm going to use the SI unit system, but I'm going to make a couple changes. I'm going to say, hey, you know what? I want to work in temperature, and I want to work in miles per hour, or temperature of Fahrenheit, miles per hour of or temperature in Fahrenheit, velocity in miles per hour. Sorry about that. I also want my geometric my loads to be, instead of in angles, I want it to be in degrees, and let's leave it like that for now. So that's all I'm going to specify. Now you can always create your own unit system. You can see I have one down here called OZCFM. That's one that's kind of customized for cubic feet per minute for a lot of internal problems. Now the next thing that it asks is, hey, do you want to do an internal or an external analysis? So I'm going to say I'm going to do an external analysis, which means I want flow moving over the system. These images are reversed, I think, just to keep people on your toes. Internal is actually the bottom image, external is the top. Here are some advanced physics. So if you wanted to include heat conduction, radiation, which could be solar radiation, or surface to ambient, surface to surface. We could include gravity or rotation. The gases, there are a whole bunch of predefined gases. You can always create your own predefined liquids, non-Newtonian liquids. I'm going to go with air. If you knew the surface roughness of your drone and you wanted to account for the surface roughness, you know, in the turbulent boundary layer, you could account for that here. And finally, it asks, hey, okay, well, what do you want your thermodynamic parameters to be? So, you know, if this drone was flying at, you know, up in space or up in the atmosphere, obviously it's going to have a different pressure and different temperature, so you could specify that here. But the most important thing, or one of the most important things for an external flow analysis, is it wants us to specify the velocity, basically, the wind speed. So the way I like to do this is, instead of doing a vector, what I often do is I'll go to an aerodynamic angle. And the plane that I want to work in is the ZY plane. So I'm just going to switch to my ZY plane. The direction that I want to be longitudinal is the Z-axis. And I'm going to say, let's say I want an angle of attack of 10 degrees. Oops. And I want a wind speed of -100. Oops. And I pressed slightly too quick there. Let me go back. This arrow represents the direction. It's basically your angle of attack. Now, angle of side slip is, you know, just the angle kind of, you know, rotating about the y-axis. So if I put a 10 in here, very obvious what that is, right? Now, the nice thing about setting it up this way is, if I want to do a parametric study where I vary the angle of side slip or the angle of attack, it's real easy to do that. Whereas with vectors, it can kind of be a little bit more confusing. So let me just say OK. And now you know, that's basically all I really need to do to set up an external flow analysis. This box that just was created is my computational domain. So I can make it larger. You know, a lot of times for external problems, you want to make your computational domain larger or smaller. It automatically does your Booleans for you. It knows where fluid exists. It knows where solid exists. And the only thing you'd have to do next is you would add some goals. So let me hop into a problem that's already solved, just because, you know, we don't have time to go through a full setup. And, you know, I'm not doing anything fancy here. Here's my computational domain. If I come here to the general settings, you can see my initial settings, -100 degrees. I've got a 10-degree angle of attack. Now, one of the things I want to point out, like Ron mentioned, you know, I used to work for one of our competitors, and one of the things that we struggled with quite a bit was, you know, generating a mesh. So, you know, if you guys noticed, let me hide the mesh just real quickly. I have these cylinders that are going around my drone bodies. Now, the reason that I've done that is because in my initial setup, I'm actually putting on some local initial meshes. So if I come in here, I'm actually grabbing that body, and I'm saying, look, all of the cells in that body, I want you to refine once or twice or however many you want. Now, in addition to that, I'm coming to my component controls, and I'm telling the solver, hey, these bodies, do not include them. They're not solids. They're simply there for a mesh setting, or they could be a place where you wanted to monitor results. So you've got that kind of control. There are lots of different mesh controls that you can use. The other thing that you do is I set up some goals. So for instance, I set up a goal for drag. And what that drag goal is it's just summing all of the normal forces on the solids in the y direction, and I'm using that for convergence. So you know, anything that I'm really interested in, whether it's drags or temperatures on components or average velocities or you know, lift, all of those things, I can create goals, I can create equation goals, and then I can ensure that I've got a converged result. So let's start looking at some of the results here. Now, let me just show all of these, and then we'll turn them off individually. So the first thing that we're looking at here are what are called cut plots. Now, cut plots, you know, just like the name entails, they basically look at a cut plane through your system. So, and I can customize the cut plot. If I come in here and say edit definition, for instance, I can turn on the mesh on a cut plot. It should be obvious here what those cylindrical regions are doing now, right? I'm refining the mesh in there. Another nice thing that you can do is you can turn on streamlines in a cut plot, and that shows you exactly how fluid is moving. Oops, on that cut plot, let me go back. I turned off contours. So we can see exactly how streamlines are moving. If I zoom in, you can see that the streamlines get finer and finer. So it's a nice way, you know, if you're searching for areas where you might have recirculation, this is a great way to kind of identify that. I can click play on a cut plot. It moves that cut plot back and forth through my system. I don't have to look at pressures. I can look at things like velocities. I can look for, Mach numbers if that's something that I'm interested in, to look for high Mach number areas. So you can get a lot of different information. Another nice plot that you can look at is something called the surface plot, right? And in this case, I'm just showing the pressure on my drone here. And then finally, the one that's really interesting in flow simulation that you really can't get in a finite element analysis is flow trajectories, right? Oops. So flow trajectories actually show us how and the goal plots show us, what our lift, drag, and average velocity is in this case. Let's say that I know this drone weighs 1,500 pounds. I can see here that with this length of wing, I'm getting a lift force of 2,200 pounds. So I could potentially argue that this thing is over-designed. So one of the really powerful things that you can do with a simulation tool that's embedded inside of your CAD package is I can run a what-if analysis. Now, this particular what-if analysis, because this is an imported body, I had to do a little bit of gymnastics here. What I did is I created a plane. And I basically am offsetting that plane different values to bring it in, 5.2 meters, 5.7, 6.2, 6.7, and 7.2 meters. Then I'm cutting the wing, and then I'm mirroring the wing to the other side. So it's a way to look at smaller wing geometries, basically. And I'm asking it to run all of these different scenarios for different wing lengths and tell me what the lift is. And you can see, so the default here, 7.2 is about 2,200, 5.2 is about 1,800. So, this is a way to explore your design space, right? This is just one specific example of how you could potentially do that. So let me just close this guy, and let's pop back into the presentation. So hopefully, that one made sense. Again, that is just a very, very basic flow and geometry study. Now let's take a look at a slightly more advanced drone configuration, right? So here we're looking at essentially the same drone, but now we've got, more of the correct geometry basically added to it. And actually, this isn't even the most complicated one. Let's actually, let's take a look at this one. So same exact setup, and now I can take a look at some of these results. Now I haven't added rotating region yet. That's something that I'll show you guys in another example, how you could potentially add that. But if I wanted to, I could include the rotation of this propeller back here, which you probably would want to with in a model like this. The way I like to approach these kind of problems is I like to start simple and then add complexity, right? Because obviously the more simple the study, the faster you can go through and get results. Now what I did do in this case is I ran a what-if study. And just so you guys understand, your what-if study doesn't just have to have one parameter, right? So the first one, the parameter was the length of the wing. And this one, I'm changing the angle of attack from 10 to 30 degrees. You could include both of them at once, right? So, and you could have multiple input parameters. It's just going to create a design of experiment and run all of those different design points for you. So, depending on the complexity, this could be something that you maybe would run over the weekend, or, like I said, I live in Southern California, so maybe do it over lunch and go surfing or whatever it is you like to do, because your boss is going to come in there and see that your computer's running, so you're going to be in fine shape. But the nice thing here, right, I think I remember reading that this drone weighs somewhere between 2,000 and 2,500 pounds. I think it was closer to about 21 or 2,200. So we can see that if we want this thing to take off, we need to be hitting it with an angle of attack between 20 and 25 pounds. And then I went and ran there's another configuration here that has your Hellfire missiles included. It's got your gimbal, your camera down here, and a separate what-if study here, just to verify that with these additional components that we're not going to be taking away from the lift, and we can see the results for that. And then again, a really nice thing about flow simulation is if I've got it set up for one of my configurations, here's my flow configuration, I can just right-click and say clone, and it's going to tell me, okay, what configuration do you want to clone it to? So if you have multiple configurations, you can create like a master flow configuration and then copy that flow configuration, all the setup, meshing, post-processing into all of your other configurations. So let's just pop back into the presentation. Yeah, so we do an angle of attack study basically for the two different drones. And then let me show you guys a couple more things. I know it seems like I'm perpetually running out of time on these webinars. I think I might talk too much. So let me add SOLIDWORKS simulation because I want to show you guys another really, really interesting thing that you can do. So basically, I've turned on the FEA solver, and what I'm doing in the FEA run here is I'm actually pulling the loads from the fluid run. So I'm saying, look, I want to grab the pressures from that flow simulation, and I want you to map those pressures onto my structure here. So here is my fluid pressures. And the meshes are completely different, right? The mesh from the flow solver, completely different than the mesh from the FEA solver, right? You're not going to have, the types of meshes that are adequate in both cases are very, very different. So it does a 3D interpolation to get the correct pressures on here. And now I can, I said that this is a very basic setup. I just basically fixed this guy at two places, at the center up here and this back face. And now I can take a look at the stresses. Now this deformation is scaled about 100 times, but this is basically a fluid structure interaction problem, right? So I'm taking into account the pressures, seeing how much stress, displacement that those are going to cause. Now bear in mind, right, that the way this model was set up, all this stuff is considered solid, so you're going to want to have an accurate geometric representation. For flow, it doesn't matter as much because you're just looking at flow around the body. But if you're going to be doing a structural analysis, right, in order to capture the correct stiffness, you want to make sure that you've got, the proper geometry, right? So I think we got one more thing I'm going to show you guys. Yeah, we showed this. So now let's take a look. I really wanted to get to run this full the four propeller drone. I didn't have a chance to quite do that. What I did do is I set up a single prop, and I ran a flow simulation where we actually take into account the rotating region. So in your setup, there's a rotation, and there are some different ways that you can capture rotation. There's a sliding mesh, there's a local rotation, and there's a global rotation. So what I've done is I said, hey, look, this thing is going to be rotating at about 1,200 RPM. And let me just show you guys some of the results here. And we can take a look at what exactly the results look like. So we can see the flow coming through the propeller. And that's, obviously that's nice. But really what we're probably interested in is, hey, how much, maybe torque is that generating? So you can see the torque in the Y direction is, whatever it is. Don't worry. The number is not as important here. As it, just showing the physics. So let's say, maybe I'm assuming that I want to use a 2-propeller system. Maybe I want to also look at 3 propellers or 4 propellers, or change the geometry of the propellers to try to get some desired torque or thrust, right? All things that you can do inside a flow simulation. So let's see, how late am I? All right, just a couple minutes. So I think now we're going to do the second poll question. And as Ron is asking this one, I am going to do my best to answer some questions. And I will answer them out loud. So, can CFD calculate ducted fan performance? Yes, it can, absolutely. What version of SOLIDWORKS is being used? Oh, Ron answered. So our FEA, there's a question here about using modeling composites in our FEA solver. You can do that. It's with a product called SolidWorks Simulation Premium. You know, and it's basically you model it as a shell, and then you put in your layer stack up. So you put in each layer, the material property, and the fiber orientation. Compression molding. No, flow simulation can't be used to model that, but that has been coming up quite frequently in our plastic injection molding software. So you could potentially do that. Can I set up Excel to drive an automated optimization? So you can't. You wouldn't use Excel. You could do design tables inside of SolidWorks, or you could use you know, basically our parametric study is an Excel file, so you could cut and paste the values from your Excel file and then use them.
Omar, we've completed the second poll, so if you have more slides too.
Okay. Let me just delete the ones that I've answered here, and then we're almost done. All right. So hopefully, you know, that, again, real quick, these webinars are meant to only be about 22 minutes in length, but hopefully you guys see how, you know, using really any design validation tools, the more that you can virtually test things on the computer, and, you know, I'm a simulation guy, so, you know, whatever tool you're using, I really love SolidWorks simulation and the tools because they're, first of all, I guess they pay my check, but second of all, because they're embedded inside of SolidWorks, I've just found that they, it allows you to really take advantage of the CAD model in a way that you can't do in a lot of other packages, right? Changes that are made on CAD are just automatically taken into your flow or FEA analyses, and it just eliminates a lot of the redundancy. And you know, this is a graph that we pulled from a business website just saying that, you know, it's better that a product is expensive than late. So the quicker that you can get to your design, to your final design, the better off that you are, even if it costs a little bit more. Consumers are willing to pay a higher premium. All right, so that being said, Ron, I think you have a couple more poll questions, and as you're doing the poll questions, guys, I will continue to answer questions as quickly as I can. And
yes, we have the level of interest in learning more about what you've just seen. Obviously, this is less than half an hour, and Omar whipped through a lot of information quickly. So, you know, the purpose here is to just kind of give you general overviews. Tomorrow, we're having an in-depth 1-hour seminar given again by Omar about flow simulation. So please join us if you'd like to get more details.
All right, so the lift value is actually for the whole assembly. It's not just for the wing, but I mean, if you're changing the wing length, obviously the lift value is going to change. I will provide some contact information in a second here. Cost of the add-on, Daniel, it's probably better that you talk to your reseller. You know, I'm on the technical side. I assume all this stuff is free. But you know, your reseller will be able to tell you what specials are going on. I have no idea. I wouldn't even want to venture a guess. The next plastics webinar, do you know when that is, Ron?
You know, we run so many. I don't offhand. I'm sorry. If you want to contact myself or Cliff Medling or Omar, we'll find out when that next plastics webinar is. The one that I can recall at the top of my head is we're doing one on September 30th.
And all right, so a couple people asking for my contact information. Here it is, guys. I'm responsible for all of North America, the simulation tools all throughout North America. So, you know, feel free to send me an email or give me a call. Yep. Omar,
I'm sorry. I have the last poll question up, and we'll just do this for another few seconds.
Okay.
And then you'll be able to put your slide up.
So yes, you can view this later. This is recorded. You guys can come back in here and you'll be able to watch it, I guess, as soon as it gets uploaded today or tomorrow. Ron will send an email, I believe.
Yeah, we typically send an email 1 to 3 days after the webinar is held. We have to process the recording, and then sorry, there you go, Omar. And then post it, and then send the email out. So it's usually between 1 and 3 days. Everyone will get a link.
All right. Well, thank you guys for joining. And again, let me just. Yeah, it looks like my contact information is up. So, you guys have any questions? Feel free to send me an email, and I will. A couple of people asked for the geometry. I had to just figure out the models are a little bit big, so I have to figure out a way to best get that stuff to you. And someone asked about the graph from that business article. I will grab that for you. And if you send me an email, I'll grab it and respond to you. So.
Well, with that, thank you very much, Omar. Thank you, everyone who joined. We appreciate your interest in SOLIDWORKS, and have a great day.
Thanks, Ron. See you guys. Thanks again.
Thank you.